comb generation using gain switching. So first, let me give you a brief introduction about myself. I did my undergrad in physics in UCC. Throughout that time, I have done 2 internships and my final year project here in Tyndall. And I started my PhD on the development of a chip for frequency comb generation in October 2019. So how this talk is going to go is first I'll give you an introduction to frequency combs and gain switching. Then I'll move on to how combs can be simulated and how their quality can be improved by varying certain factors. Then I'll talk about the photonic integrated circuit design and how it was modeled. And finally, I'll run through the experimental work. So let's begin. So why do we want frequency combs? Well, modern optical networks use hundreds of separate lasers which fill up the limited bandwidth. The channels in the spectral bandwidth are separated by empty regions called guard bands. Their purpose is to prevent one channel from interfering with another. For example, if one channel begins to jitter, the guard bands are large enough that the jitter doesn't affect the next channel. The problem is that these guard bands are spectrally inefficient, and due to the increased demand, the bandwidth has become more and more limited. Optical frequency comb sources can potentially reduce or eliminate these guard bands. Optical frequency combs are used to generate a number of precisely spaced spectral carriers that have a precise and stable frequency. Due to the fixed phase relation between the carriers in the comb, there is no interference between comb lines. In other words, if one comb line jitters, then all comb lines jitter. So the method I use to generate my combs is through gain switching. So what gain switching is it takes advantage of the relaxation oscillation phenomenon which occurs when a semiconductor is biased abruptly. This phenomenon is demonstrated by the plot on the left, where the carrier and photon densities present a transient response with damped oscillations before eventually reaching a steady state. But I achieve my combs through gain switching, which involves operating the lasers in the initial nonlinear regime. This is achieved by modulating the biased current applied to the laser with a high-power radio frequency signal, effectively creating a sinusoidal current, which the frequency is equivalent to the applied RF frequency. So what this sinusoidal current does is operate the laser in the nonlinear regime by turning the laser on and off, so that only the first excited pulse is generated before the device is turned off and on again, effectively creating a pulse train in both the carrier and photon density. So now I'm going to move on to simulating a comb, and from there I'm going to look at various parameters that will affect the comb and ultimately determine what can be done to optimize them. So first, I'm going to look at the carrier and photon densities that can be derived from the rate equations. This is similar to what I showed you in the previous slide, where we have carrier and photon density before and after gain switching. So to simulate the comb, I start by changing the photon density from the time domain to the frequency domain by taking the fast Fourier transform. In order to do this, a time step had to be selected whereby the data would repeat after every 2 to the n data points. So what the photon density pulse period you see to the left, there are 2 to the 8 or 256 data points. Taking the fast Fourier transform, what you get are these optical pulses in the frequency domain. And since I use an R frequency supply of about 5.75 gigahertz, the frequency separation of the optical pulses are equivalently 5.75 gigahertz. The next step is to convert these optical pulses into what we would view on a spectra by converting it to dBm, which is shown on the plot here, and so a comb has been simulated. So now what I want to achieve was to determine what conditions could be altered to optimize or improve the quality of the comb I'm generating. For example, how the capacitance and resistance of the device would affect the comb, as well as the experimental variables like the bias current and the voltage of the signal generator. Well, first, let's treat the signal generator and laser as an RC circuit, as demonstrated by the diagram below. The resulting equation of the current is given above, and so we can examine how certain parameters would affect the RF current and then determine an idea of how this would affect the generated combs. So we want to see how the parameters determined by the fabrication run, like resistance and capacitance, would affect the generated combs, as well as the experimental parameters like the RF voltage and the bias current. So let's have a look at resistance first. This three-dimensional plot represents how the current in the time domain changes as the resistance is varied from 1 ohm to 14 ohms. The color represents the current with time on the y-axis and resistance on the x-axis. I also have a three-dimensional plot of the current through one oscillation period for your convenience. So there's nothing unexpected here. The resistance affects the RF current in the sense that there's an increase in the maximum current as the resistance decreases. So I did the same thing for capacitance, and it's pretty much the same story. The amplitude of the current increases as the capacitance decreases from 114 or 1400 femtofarads to 1 femtofarad. Moving on to the experimental effects, starting with RF voltage, the RF effects increase as the RF voltage increases. And finally, with the bias current, as we would expect, it did nothing to affect the amplitude of the sinusoidal current itself, but rather shifted the sinusoidal current with the equivalent bias current. So why am I showing you this one? Well, as you can see from the plots, as the bias current increases, so does the minimum value of the sinusoidal current. This suggests that there comes a point where the minimum value of the sinusoidal current can increase above the threshold current of the laser. As a result, the laser can no longer be switched off. And since gain switching only occurs by switching the laser on and off, there comes a high enough bias current whereby a comb can no longer be generated. Excuse me. So moving on to how these parameters affect the quality of the generated combs. To measure the quality of the comb, I used a parameter called delta F10. Now, what this represents is the frequency range the comb lines occupy within 10 decibels of the center peak. So naturally, a good quality comb would have a rather high delta F10 value. So I wanted to see how the parameters I've mentioned, like resistance, capacitance, bias current, and RF voltage, would affect the comb's quality. For convenience, the following simulations are run using an RF frequency of 6 gigahertz. So this is another color plot showing how the resistance and capacitance affects the comb itself. The color represents delta F10, with capacitance on the x-axis ranging from 1 femtofarad to 1400 femtofarads, and resistance on the y-axis ranging from 1 ohm to 10 ohms. Based off the results attained from the current plots, we would have expected the quality of the combs to improve as we reduce the resistance and capacitance, and that is effectively what we see here. So what I'm just going to do quickly is compare this theoretical plot to what we could attain experimentally. So the plot at the bottom is an experimentally attained frequency comb with a frequency separation of 5.75 gigahertz. There are about 10 comb lines within 10 decibels of each other. So if we multiply the 5.75 by 9, we get 51.75 gigahertz. Calculating the capacitance by getting the capacitance of the active region and the capacitance between the contact pads, we get a capacitance of about 700 femtofarads, and the experimental resistance attained was 5.8 ohms. So reading this off the plot, we would have expected a theoretical value of delta F10 to be 50 gigahertz, which is in quite good agreement with what we would attain experimentally. So next I carry out the same measurement while varying the bias current and RF voltage. So what is evident in this plot is that there appears to be a clear border region that separates a region of high delta F10 and a region of low delta F10. So this relates back to what I was talking about earlier when describing how the sinusoidal current was affected by the bias current. That is, there comes a point where the bias current causes the minimum value of the sinusoidal current to no longer fall below threshold value of the device. In other words, there is a maximum value for the bias current that can be used to generate combs. So in terms of RF voltage, we know from the earlier simulations that increasing the RF voltage increases the amplitude of the sinusoidal current. This in turn would increase that maximum bias current value at which the comb could be generated. And that is effectively what we see here by the borderline. So the final component to investigate how a comb would behave is the frequency of the RF current, or in other words, the frequency spacing of the comb lines. So up until now, the simulations that I've shown was for an applied frequency of about 6 gigahertz. The eventual goal is to design a chip that can achieve a broader comb line spacing, for example, up to 20 gigahertz. So based on the earlier simulations, we can assume that we can achieve broader comb lines by reducing parameters like the resistance or capacitance. But would the quality, or delta F10, remain the same if the applied frequency is altered? So let's first look back at how this affects the carrier density. So let's first focus on the first plot, where the color represents the carrier density of the gain switch device and how it varies with time along the x-axis and the applied frequency along the y-axis. We can see that the carrier density of the device degrades as the applied frequency is increased. This gives us an indication that the comb itself would therefore be affected by a change in the frequency. I have replicated the plot to also show how it changes with capacity, and as we would have expected from the previous simulations, the carrier density degrades as the capacitance is increased. So I also did this for the photon density. As you can see here, a similar result is achieved. The photon density degrades as the frequency was increased, and I also plotted this for different values of capacitance. At this point, you can probably guess what I'm trying to do next. I want to get the fast Fourier transform of the photon density at each frequency and show how the comb lines themselves would change as the frequency increased. So that leads to this. Excuse me. The color represents the power in dBm, with the comb frequency spacing on the x-axis and the applied radio frequency on the y-axis. I plotted this for different capacitance, but the resistance was kept constant at 10 ohms. So as the resistance decreases, we should see these combs improve in quality for all frequencies. So next, I'm moving on to a photonic integrated circuit that was designed and fabricated to generate frequency combs. So here's a 3-section device. It is made up of a 2-sectioned master and slave section. Ultimately, the slave section will be gain switched, but the master-slave configuration would allow to take advantage of injection locking. These advantages include the reduction of phase noise in gain switch lasers, and injection locking on shift devices has been demonstrated to increase the side mode suppression ratio, or SMSR. So injection locking means that the slave laser will be optically phase locked to the master. The master will be more heavily biased than the slave, so while no isolator exists between the two lasers, the asymmetric bias regime would allow for injection locking. The master laser is made up of a gain and slotted section with the purpose of generating a single mode spectra. That is, that the SMSR is greater than 30 decibels. In the next few slides, I will explain how this allows for single mode behavior. So that brings us on to the theoretical modeling of the laser. How I modeled the behavior of lasers is by using transmission matrices, which is used to describe the transmission and reflection profiles of a laser cavity. There are 2 main types of transmission matrices, one which describes the transmission through a reflective surface by taking into account the change in refractive index, and the other describes the transmission through a waveguide by taking into account the length of the cavity, the refractive index, and the wavelength. So in the case of a simple fabric probe, you could find the transmission matrix by finding the cross product of 2 reflective transmission matrices and the transmission matrix of the cavity. This results in a 4x4 matrix, and the reflective profile is then T21 over T11 to be squared, and this can be plotted as a function of wavelength, which I'll show you in a few slides. For telecommunications, it is ideal that the device is single mode. An easy way to achieve this is by creating a mirror or reflective region made up of slots that have been etched into the ridge of the laser. The slots act as reflective defects by creating regions of changing effective refractive index along the ridge of the laser. By biasing the slotted region of the device, a single mode spectra can be produced, and by varying the current across the region, the wavelength of the spectra can be varied. So here's a simulation of how the reflection profile of a Fabry Pro can be changed by introducing these slots. The above plot shows a reflection profile for a Fabry Pro with a cavity length of 800 microns. The plot below shows the reflection profile of an 800 micron Fabry Pro region with an additional region made up of 8 slots with an interslot separation of 108 microns. This results in the maximum reflection coefficients created by the mode of the Fabry Pro to be suppressed by these larger modes created by the slots. A single mode wavelength can result at any of these larger modes, but whether it lasers here or not depends on the position of the smaller modes within. By changing the current through the mirror section, the position of the larger modes can shift, and when one of the smaller modes reaches the center of the larger mode, the device will lase at this wavelength. This is more obvious when plotted in a logarithmic scale. As you can see, when the mode reaches a maximum reflection coefficient, they shoot up, showing at what wavelength the device would lase. So by changing the bias current, you can change the effective refractive index of the device. This in turn changes the optical path length, and so the wavelength can be tunable. Finally, this leads me to some experimental work that I've done. So this is my experimental setup in Tyndall. Excuse me. So the device itself is placed on the probing station below. It's powered by the Keithley power supply and additional power supply above. Next to that is the signal generator, and that's modulated with the bias current that's biasing the slave section. And then the spectra itself is measured by the OSA. So here is the example I described earlier. It's a master-slave device. The master is made up of a gain section and slot section, which produces single mode. This is injection locked with the slave section. The slave section is then gain switched and a comb is produced. So this is a experimental schematic showing that the master laser is biased, injection locked with the slave laser. Signal generation and current source are modulated with a bias T, and that's what used to bias the slave laser. And then the resulting comb is measured through the OSA. So first, what I did was I measured or characterized the master section by varying the current through the slotted section, gain section, and attaining the spectra at each point. So what these two measurements are the SMSR above and the wavelength below. So as I said, we ideally want a side mode suppression ratio greater than 30 decibels. I've gradiated or made a gradient in this plot. So these orange bits, or the border of it, represent where it's 30 decibels, and then within is larger. So the border of this one would be 35. And then the equivalent wavelength is below. So another way of viewing this is by viewing the individual peaks. So with this device, I attained 9 different wavelengths with an SMSR of 30 decibels or greater, and I had a tunable range of 27 nanometers. So I could take this point to compare it with the theoretical reflection profile that I showed how to get earlier. As you can see, the peaks obtained experimentally is where the peaks of these slots are defined. So the theory compares quite well with the experiment. So after that, it was injection locked with the slave, and the slave was gain switched. So here's an example of one of the combs that was attained. It was attained at an RF frequency of 5.75 gigahertz. There are about 6 comb lines within 2 decibels of each other. So here are another few comb spectra and how it changes with the increase in frequency. So as you can see, it starts with 5.7 or 6.5 gigahertz, 7.1, 7.7, and 8.5. And what you can see is as the frequencies increase, the frequency spacing between the comb lines increases equivalently, but the quality of the comb degrades. I have a three-dimensional plot here that was obtained experimentally, showing how this decreases as the R frequency increases, which is what was theorized or attained theoretically in the previous simulations. So that concludes my talk. Thank you all for listening.
Thank you, George.